Class, I want to cover section 2.2, the limit of a function, and limits are crucial in Calculus 1. Very important that you understand this. So the definition of a limit, and I know this is kind of hard to see, but this says the limit of f of x as x approaches a equals L. Okay, so what that means is the limit of f of x as x approaches a equals L. So what that means is we can make the value of f of x arbitrarily close to L, or as close as we like, by taking x to be sufficiently close to a on either side of a, but not equal a. So x is getting closer and closer to a from coming in from numbers less than a and coming in from numbers greater than a. And the function, as that happens, is getting closer and closer to some number L. So this means ignore what happens when x is equal to a, but as x gets closer and closer to a, f of x gets closer and closer to L. So, for example, this has already been graphed on the calculator. Let me write out what this actually is. Okay, so the function here is f of x equals x squared minus 2x over x squared minus x minus 2. Okay, so first question is, where is f of x undefined? Okay, so, functions, there's different ways that functions can be undefined, but when you've got a rational function, that's what this is called. When you've got x or some kind of expression involving x in the denominator, that's going to be undefined when the denominator is equal to 0. Well, that's a quadratic equation, and we can solve that by factoring. It factors into x minus 2 times x plus 1 equals 0. So that means, by the zero product principle, if you have two factors set equal to 0, then one or both of them must be 0. So just remember this from college algebra. So we get x equal 2 and x equal minus 1. Now that's where it's undefined. This is where f of x is undefined. Now, if we look at the graph up here, we can see that this is where x is equal to -1. And this right here is on your calculator. It might put a line here. It might put little dash lines, but this is a vertical asymptote. So you studied vertical asymptotes in college algebra and probably also in trig. So what the function is doing, what f of x is doing, is it gets closer from coming in from the left, it's going up, and as it comes in from the right, it's going down. And it never actually touches, so I shouldn't have it touching. It never actually touches that line. Now, what's happening when x is equal to 2? So that'd be like right around in here. It looks like it's defined there, but if we really look at on the calculator what's going on there, so let me just graph this and then be sure you use your parentheses correctly here. So it's x squared minus 2x and then put a parenthesis and then go divide and put the denominator in parentheses as well. So it's x squared minus x minus 2. Okay, and if I hit graph, got some kind of error here. Oh, it's right there. Okay, let me see if I can put an X there. And then let's see if it'll work. Okay, so that's what it looked like on our notes. Now, if you go second function calc, you can see what's going on at x equal 2. So let's go enter 2 for the x value. And notice there's no y value. What that means is it's undefined at x equal 2. So there's really a little hole there that you really can't see because we're looking at a bigger picture of the function. If you went in really, really close, I don't know if you could even do that with this calculator, but there really is just a little hole in this graph. So that's what's happening right there. Now, when we talk about a limit, when you're coming in from the left of, and this is x equal 2, when you're coming in from the left and we're coming into some point right here, and when we're coming in from the right, we're also coming into that point. See, you're coming into the same place, and you can see that on the calculator. You're coming into the same number coming from the left and the right, whatever that number is. So it means that the limit exists even though the function is not defined there. But the limit can still exist because when we talk about a limit, we're not talking about what happens at x equal 2. We're talking about what is the function getting closer to as x approaches 2 from the left and x approaches 2 from the right. Well, if we go over here and we look at our table, this is a good thing to use. And when I first go to the table, I notice I've got an error at 2. It's kind of hard to tell what's happening. But if I go to table set, so you hit the blue button and then you hit table set, you can start this like just a little bit less than 2. And then you can make this change in the table be say 0.01. And I just want to break it down so I can see what's happening as we really come into 2. And so I'm breaking it down so that we're looking at values that are really close to 2. Okay, so we see it's 0.66555 on this side. It's 0.6677. Let me change this just a little bit. Let me change this back to 1. Let's just make it 1.9. Because I want to see a little bit more of what's going on that side. Okay, so we see how the digits, the first digit's 6 on all these. The second digit is getting closer to 6. And then it actually becomes 6. And let's see if we can shuffle down a little bit. And then it looks like the third digit is getting closer to 6. There's an error right there at 2 because it's not defined. Then if you notice on the other side, that second number became 6. And then actually the third number is becoming 6. And so what it's actually getting close to, it is getting close to, so let's say it looks like the limit as x approaches 2 of this function. Scoot up a little bit. Is going to, 0.66666, but that is actually equal to 2/3. Now, later in the next section, we're going to find out how to actually show this without just having to look on our calculator and figure it out from there. So in the next section, which is 2.3, we're going to do this. We're going to factor. And so we can factor an x out of the numerator. And then we can factor the denominator, we've already done this, into x minus 2 times x plus 1. Now notice this x minus 2 will cancel with that. And then if we substitute in a 2, because I can do that now, I have 2/3. Okay, so that's what we're talking about when we're talking about a limit. Let me go to the next page. Okay, so what we're looking at here is when it says the limit as x approaches a, and it has this minus sign right here. Okay, so we're going to talk about what that means. Okay, so it says, we say the left-hand limit of f of x as x approaches a, or the limit of f of x as x approaches a from the left is equal to L if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a and x is less than a. Now what this means is, like if you think on a number line and say this is a, we're coming in with numbers that are less than a. We're coming in to x being a, but we're coming in with numbers less than a. So for instance, if you had, say right here, my cat is really bothering me right now, and that's why I'm kind of struggling here. X is going to 2 from the left. That means we're coming in this way. So numbers like 1.99. And then over here, x is approaching 2, and if we have a little plus sign over that, that means we're coming in from numbers greater than 2, like for instance, that number. Oops, turn that way. So, that's another thing. If it says coming into A, and we're coming in from, and it has the plus sign there, that means that we're coming in on this side of A. So we can talk about the left-sided limit and the right-sided limit. Now, they might not be the same, but in order for the general limit of the function to exist at A, and I'm just going to write this out because it's a little bit blurred, the limit as x approaches A equals L if and only if, and in math we use that a lot, so we just say if and only if, the limit as x approaches A from the left equals L, and the limit as x approaches A from the right of f of x equal L. So in order for the limit to really exist, you have to be coming in to the same number from the left and from the right. Now let me show you these two examples. Close enough. Here's a function, and we notice that as we're coming in, this point is 2, 2, and the function is really not defined there. If it's got that hole, that means it's not defined there. And this down here is the point 2, -1. So here we're coming in to 2. So we're approaching 2 from the left. And then over here, we're approaching 2 from the right. Now, you look at what the function is doing right here. So we would say the limit as x approaches 2 from the left is equal to 2. Because see that point that's actually not there, the y value is 2. But if we look at coming in from the right, it's going to be the y value right here, which is -1. These values are not equal in this case. So the limit as x approaches 2 in general does not exist. And in your homework, you'll put in does not exist for this. Okay. Now let's look at this other function now. And so it's a different function, and there is a hole. So let me make the hole look like a hole right there. There's a hole right here. So the function's not defined at 5, 3. So f of x is undefined at x equals 5. Okay, x equals 5. However, the limit does exist. Okay, so what is that limit? The limit as x approaches 5 from the left, well, it's coming into that point right there. And so the y value is 3. And the limit as x approaches 5 from the right of f of x, coming in from the right, and so we're talking about the y value, because we say, what is the function getting closer to? That means the y value. It's also equal to 3. These are the same value. So the limit as x approaches 5 in general of f of x is equal to 3. Okay, so another question. What is f of 5? Well, if you were in my class, you would have to tell me. But f of 5 does not exist. Okay, so that's kind of looking at limits, looking at a graph. Because you can tell by looking at a graph what's happening with the limits. Okay, let's go to the next page. By the way, this background that you see, it's actually a board that my friend had. And she would play cards while she was watching TV when she was really old. And it was her board. And it works really good for recording here. So I kind of like it. Okay, this is the previous example. But this time, and so we know already that the limit as x goes to 2 of this function was equal to 0.6 or 2/3. But what is the limit as x approaches -1 of this function? And let's go ahead and put it in factored form right here. And talk, because we're gonna be doing this in the next section. So let's just look at it in factored form, because you know we could factor an x out of the top. And we could factor the bottom. I think that was how it went. And then that can cancel. But notice that this x plus 1 does not cancel. And that is the problem, because if you put in a -1 here, you're going to get 0 in the denominator. And so what actually happens is this limit actually exists or not. If we go back over here and we look at the function, that's where the vertical asymptote is. So it does not exist there is a vertical asymptote. And when there's a vertical asymptote, it's going to go up to infinity or down to negative infinity. Both sides may be going up to positive infinity, but it's going to involve infinity. So we can say it's true, the limit does not exist. It does not exist. But let me move my calculators in the way. So, but what we can say that the limit as x approaches -1 from the left of f of x, well, from the left, if you look back over here, it's going up to positive infinity. But the limit as x approaches -1 from the right of f of x, well, that's on this side. It's approaching, and notice the function is going down, down, down. So we would often say this, and it's still true that the limit doesn't exist. However, we can use this to say what the function's doing, you know, how it's going. So it still does not exist. If the answer is not a number, because remember, if the limit exists, then it's a number that it's getting closer to. So if it's infinity or negative infinity, the limit really doesn't exist, but we can talk about it this way. And we often do. Okay. Let's look at the next page. We're going to talk about limits on a graph a little bit. Okay. Now, here's our function. Really seem to get the whole thing. Okay, so for the function g, and this is the function g of t. For the function g whose graph is given, state the value of each quantity if it exists. If it does not exist, explain why. So if we were in class, I'd be asking you to help me with this, but unfortunately we're not. So that's a hole right there, and there's a hole right here too. But this is actually a point right there. So first of all, we look at the limit as x approaches 0 from the left, because it's got the minus sign. So we're coming into 0 from the left. And notice, what is that y value right there? It's -1. Okay. Then the limit as x approaches 0 from the right, well, it's coming into this y value, which is -2. Okay, then what's the limit as t approaches 0? Well, okay, for the general limit without the plus or minus to exist, you have to be coming into the same place from the left and the right. And you can just see visually that they're not coming into the same number. So this does not exist. Okay, then we've got the limit as x approaches 2, and this is from the left. I hope y'all can see that. And x approaches 2 from the left. So we're looking like right here. What's the y value? The y value is 2. And then this one has the little plus sign over it. So we're coming into 2 from the right, like this. And what's the y value right there? Well, it's 0. And then, so what is the general limit as x approaches 2? Same situation here. There's a gap there. They're not coming into the same number. So it's going to be a does not exist. Okay, then what is g of 2? So when we look over here at g of 2, oh, I left something out. Well, no, I didn't leave it out. You just can't see it. There's a point right there. That is actually, the y value there is g of 2. That y value is 1. So this is equal to 1. What is the limit as x approaches 4? Well, that's over here. And notice, you know, there's not a gap or anything. So it's just the y value there, which is 3. Okay. Let's look at another example with a graph like this. Okay, another graph. There's a hole right there, so I'm just going to draw it in so you can see it. There's a hole right here. Now that's a solid dot right there. Okay, so same thing. We want to look at the limit as x approaches 2 from the left. It's going to be that y value. And so that y value is, it's 3. So you see 1, 2, 3. That's the y value right there. And that point is the 0.23. Then it says, what's the limit as x approaches 2 from the right? What are we coming into right here? What is the y value? It is equal to 1. And I always pay attention what, you know, sometimes these graphs are counting by 2s or whatever. Always when you look at a graph, try to pay attention to that. Sometimes I forget to do that too. But the limit as x approaches 2 from the right is going to be equal to 1. So what is the general limit, which is what I call it, as x approaches 2? Well, it does not exist. What is f of 2? Well, f of 2 is going to be where the solid dot is. It's going to be the y value. And so that's equal to 3. Now, what is the limit as x approaches 4? Okay, there is a circle there, a hole. But notice that the limit as x approaches 4 from the left is equal to this y value, which is 4, and the limit as x approaches 4 from the right is also 4. They're both coming into 4 there. So what the general limit is that common value, because these are equal. Okay, then what is f of 4? It doesn't have anything where x is 4 with a solid dot, so it does not exist. It's not defined. Okay. Next page. My great aunt's tray. It's got kind of a neat pattern. I think it must be from the 30s, or it might even be from the 20s. Okay, so let f be a function defined on both sides of a, except possibly at a itself. Then the limit as x approaches a of f of x equals infinity means the values of f of x can be made arbitrarily large. So the y values are getting bigger and bigger. So as large as we please by taking x sufficiently close to a, but not equal to a. So let's look down here. So in this graph, we see there's a vertical asymptote right here. So, you know, usually when we've got x, the function going to infinity, I think pretty much all, well, not always, but when it's not defined and it's going to infinity, it's usually a vertical asymptote. So there's a vertical asymptote. And that, of course, means the function's not defined there. So another notation for this is that f of x is going towards infinity as x approaches a. Again, the symbol infinity is not a number, but the expression, the limit as x approaches a of f of x equals infinity, is often read as the limit of f of x as x approaches a is infinity, or whatever. And so increases without bound as x approaches a. So this is just an example of that. The limit as x approaches a from the left is infinity. The limit as x approaches a from the right is infinity. So the limit does not exist, but we can say the limit as x approaches a of f of x equals infinity. It could be that it's negative infinity as well. It could be that it's going down. In this case, it was going up on both sides, so we can just say that the limit is infinity. If one side was going down, we couldn't say anything about the general limit. We'd have to talk about what it's doing on the left and what it's doing on the right. But just remember that the limit as x approaches a does not exist because we're not going towards a number, we're going towards infinity. We can say this, and we do say this, but remember, unless that is going towards a number, then the limit really doesn't exist. See what else we got here. Oh, another graph. Okay, let's look at this one. Here is a graph, and I went ahead and this didn't come out very good. You really couldn't read it, so I kind of filled in what it said. And this is the graph down here. So we want to see it, we want to find these limits if they exist. So the first one says we're approaching -3. Oh, and let me draw in my holes so you can see which ones are holes. I think that's a hole too, and that's a hole. Okay, so if we're approaching -3 from the left, the y value that we're coming into, oh, and I should put this in. So this is 1, this is 2, this on the line right here is 3, and then that's 4. Okay, so this point is actually -3, 4. And notice it's not really that point, it's not part of the graph, but the limit as x is approaching -3 from the left is 4. Okay, and then the limit as x approaches -3 from the right is also 4. Those are the same. This is a 4. They're both 4. So then the limit as x approaches -3 in general is 4 because these are the same number. You get 4 and 4. Now, what is, and this graph is h of x, what is h of -3? That means what's the y value when x is -3? Well, there's a hole there. So that means it does not exist. Then here, oh, yes. So what's the limit as x approaches 0 from the left? Well, as we approach 0 from the left, we're coming in right here, coming in like this, and the y value is coming into a 1. And then what is the limit as x approaches 0 from the right? This point down here is 0, -1. And so we're coming into -1. So what is the limit as x approaches 0? We're not coming into the same place. The left-sided limit and the right-sided limit are not the same. So this does not exist. Okay, then what is h of 0? H of 0, let's see, if that's a hole, then h of 0 does not exist. Now, then what's the limit as x approaches 2? Well, look over here at 2. Coming in from the left, coming in from the right, you're coming into the same number, which is a 2. What is h of 2? There's a hole right there. That's the point 2. I think it's 2, 2. It should be 2, 2. So it does not exist there. And then we've got the limit as x approaches 5. And so here x is 5. Coming in from the right, we're coming into this y value, which is 3. But coming in from the left, this is what's called oscillation. I hope I can spell that right. And what it's actually doing, the y value is going back and forth between, I think, -4 and 2. It's oscillating right there. When that happens, that means it does not exist. Okay, so the function is oscillating as x goes to 5 from the left-hand side. So the limit does not exist. And we'll see some examples, other examples of oscillation. Matter of fact, I think I've got another one. I should just say does not exist. Oops, sorry. Can't see that. There we go. Okay, let's see. Let's look at another example. So this is an example of an oscillating function. It's f of x equal cosine of 1 over x. That's the function that is graphed. So the function is oscillating so the limit as x approaches 0 of f of x does not exist. Now, it's you know, in the other example, it existed on the left-hand side, but not the right-hand side. But now we've got oscillation on both sides. And if you graph this on your calculator and you kind of zoom in, you'll see it's going back and forth. And we can look at it right here, cosine of 1 over x. And guys, remember to always be in radian mode. When you are in this class, just always be in radian mode. Now you can't really see what's happening that much right there, but if we zoom in, we ought to be able to see the oscillation. So we can see that there. What else do we have? I want to look at a piecewise function. We look at piecewise functions a lot when we're talking about limits, and then when we're talking about continuity. And you know, you study these in college algebra. But this is a piecewise function. In this case, f of x has 3 pieces, and it's graphed over here. This is f of x equal x. This is f of x equal x squared. And this could be, I can say f of x or I can say y here. It doesn't matter. Let's just be consistent though. So I'll say f of x. And this point right here is the point 0, 2, and it is part of the graph. So if you look over here at the way it's defined, what this means, and I'm just going to do this time just to review a little bit, y equals f if x is less than 0. So you see right here, x is less than 0 and y is equal to x. Y equals 2 if x equals 0. And so you see when x is 0, the y value is 2. And then the other one, y equals x squared, if x is greater than 0. And that's the side over here. So that's a piecewise function. Now, sometimes it's interesting to talk about these functions when we're talking about limits. So, you know, so that I have more room here. The limit as x approaches 0 of f of x is 0 because it's coming into 0 from the left and the right. But we can see that the limit as x approaches 0 from the left of f of x, we would use the first piece here, and it says y equals x. So that's the same thing as the limit as x approaches 0, y is equal to x. If you substitute 0 in there for x, you get 0. Now, we can also look at the limit as x approaches 0 from the right. So you can see it's coming into 0, but you also, now notice it's actually the third piece, because it's not when x is 0. If x is 0, it's 2. But when we're talking about the limit, we're not talking about at x equals 0. We're talking about the values. What are they getting closer to as x comes into 0, in this case from the right? Well, what that would be the limit as x approaches 0. And this says the y value would be x squared. So that's going to be x is coming into 0, 0 squared is 0. So you see that these are the same. What that means is the limit as x approaches 0 of f of x equals 0. Now, what is f of 0? Well, f of 0 is 2. Okay. Okay, here's one you should try on your calculator, and if you have some in your homework that you should be trying on your calculator, you need to learn how to use your calculator to determine limits. We're going to have other ways to determine limits, but well, using algebra basically. And then also we're going to have something else for certain type of limits. But, you know, even if you use another method like algebra to find the limit, if you can, it's always good to use your calculator to verify things. I do that all the time. So, you know, like I like to know for sure, I'm sorry, I just made that worse. I like to know for sure that I'm right about something. Maybe it's a type of insecurity or something, but I like to have more than one way to know that I'm right. And so I may do it algebraically, and then I may do it with calculator. So it's good to know how to do it both ways. Now with the calculator here, and do be sure if you can always check and make sure you're in radian mode. So you can just hit the mode. Okay, so I have to use parentheses, and that's a big mistake I see students making. It's not using the parentheses, and then the calculator is going to follow the, you know, the rules for evaluating numbers. So I'm going to put an X up there, and then I have to get out of the exponent, and I'm going to go subtract 2 and raise that to the X, and then get out of the exponent, close the paren, then I'm going to divide. You don't need a paren here because you can put one, but if it's just one term, you don't really need a paren. And then I'm going to go graph it. And so we were talking about as x goes to 0. Well, we could, that isn't what I want to do really. I could trace and look at it that way, like right there, it's 1.6. And then if I go a little bit to the right of that, that's where it's actually undefined at x equals 0. And you can see why you're dividing by 0 right there. But what if you go a little bit to the left of that? It's 1.39. So it's really kind of, you know, it's coming into the same place. You can see that. But maybe if we go look at our table, let's see. I don't want it to be like that. I want it to be approaching 0. So I'm going to go and set my table. Let's come in from a negative 0.00, or let's go 0.01. Okay, and then let's let the change in x be 0.01. Let's try that. And so now I'm going to go to my table. And see, there's an error right there. So it's like coming in, I want to come in, let me come in, put more negative values there. So let me go second function table set. Let me make it minus 0.06. Okay, so we see these values coming into 1.48. Wonder if it's coming into 1.5. Let's look on the other side. Those numbers are getting closer to 1.5. So if I had to guess, I would say it looks like I'm so sorry. It looks like as x goes to 0, the y goes to 1.5. So then that means we could say the limit as x approaches 0, let me close this, of the 9 to the x minus 2 to the x over x equals 1.5. That's what it looks like. All right, that's the end, I believe, of our class for today. So guys, be sure you're doing your homework. Try to come to the WebEx session on Thursday. Be sure you're getting into website and doing your homework. You can use the free access code for 2 weeks unless you've already used it in another class. And then it won't let you use it. You might could call WebAssign and maybe they would let you use it temporarily. So also please email me if you have any questions at all. So I think that's going to be it. So I'll see you later, guys.